Now, before we go into our demonstration sessions on high resolution imaging in two of our microscopes, the JEM 2100 lanthanum hexaboride TEM, we've not been very successful in getting high resolution images from this because of the current state of the filament, and on the Geol F200 microscope. Although we were not able to successfully get high resolution images, we've still shown the procedure on how you would get on the 2100 instrument and on the F200 instrument. Now, before we go into these sessions, I'd like to give you a brief overview of the sequence of operations that you need to do before you start obtaining high resolution images. So, if I look at the microscope, the first thing you need to do is, after you insert the holder, you start with the basic alignments, which is aligning the condenser aperture, bringing the specimen to the eucentric height, and then the most important thing is orienting the specimen into the zone axis. In order to obtain high resolution micrographs, the first thing you need to do is orient the crystalline specimen into the zone axis as perfectly as you can. So, when you align the crystal into the zone axis and you look at the spot diffraction pattern, it would appear somewhat symmetric like this. And once you do this, on the grain on which you've aligned, you have to actually go to an amorphous area and you have to start doing a few corrections. The first thing that you need to correct is actually something called as the rotation center alignment. If you are using a Thermo Fisher microscope, there is something called as voltage centering, and there is something called as pivot point correction. But if you are using a Geol microscope, you have to do the HT wobble correction or the bright tilt correction. So, what you are doing is, by using this HT wobbler, you are seeing as a function of the change in the lens currents how the image is moving. You should ensure that the image distortion is not randomly in any direction in the XY plane, but it remains more or less in and out of plane along the Z axis. And once you correct for these, what you should then do is start imaging in the high resolution mode. So, after you do the voltage centering and the HT wobble corrections, there is something called as the correction of the objective astigmatism. So, if you recollect how the objective astigmatism, how the contrast transfer function looks like, by looking at an amorphous area and the Fourier transform from an amorphous area, you can start correcting for the distortions that you get from this kind of a region. So, let me quickly show you how this looks like. So, if you recollect these images from our discussions on the contrast transfer function, these are obtained from an amorphous region from a specimen. Typically, on every sample you have some amorphous region from which you can get this sort of information. If my specimen is defocused where I can start seeing these sort of ring patterns, if there is some kind of an aberration, these rings are sort of distorted in one of the directions. By using the stigmation coils, I can actually correct for them and make them as circular as possible. Once I make them really circular, I have to go over focus and under focus and ensure that I have a coincidence between these rings on either side of the focus value. That is when here is a grain on which I potentially want to get high resolution imaging. I first orient it into the zone axis following the procedures that has just been told you. And what you need to do is a couple of additional alignments. One is the HT wobble correction. If you are using a Thermo Fisher microscope, what you do is you have something called as the pivot point correction. So, you select the pivot point X and pivot point Y, and you go to a magnification of over 100,000x, and you see that the pivot points are aligned, and there is something called as rotation center alignment in a Thermo Fisher microscope. Similar to that rotation center alignment, you have something called as high tension wobble here on a JL microscope. Now, it is important that you spread the beam, put a feature of interest in the center, and let me show it on the small screen here. So here is the feature of interest, the dark shadow that you see in the center, and I'm at a magnification of 120,000x now. And at this magnification, by spreading the screen completely, I do HT wobble. What you see is, at the center, the feature of interest is moving in somewhat upward direction. From this particular camera angle and the way you see it, it might be a bit difficult to comprehend, but what you should see is the shadows that you see here, the bright and the dark shadows you see on the large screen here, they should all coincide at the same point and it should remain in the same plane. Now, a similar thing is done in rotation center alignment in a thermofission machine. You do not have pivot point correction here on the JL instrument. So what you do is, you select this, you click on HT wobble, you select the bright tilt button, and then you have to adjust it such that you'll never have a complete 100% coincidence here. Might be a little difficult to comprehend on the large screen at this angle, but as you can see here, the edge of the sample, it should appear as though the shadows or the Fresnel fringes that you see are coinciding. Please focus only on the small screen. It appears like the feature of interest remains at the same place, but it is moving up and down. This is the kind of situation where your bright tilt or the high tension wobble is now corrected. After you do this, you should always find an amorphous area in the specimen, and you have to do something called as objective stigmation correction. Let us see how that is done now. So I bring the specimen to the right height. So after you've done the HT wobble correction, what you have to do is find one of the edges of the sample. Typically, in most of the iron milled specimens or even electropolished specimens, at the edges closest to the hole, you might find some region like this. And what we do here is, we go to this region, we take a Fourier transform from the area, from the amorphous area, and we try to correct for objective stigmatism. For this, I'd like to draw your attention to the screen now, and I'll show you what is done. So once I've identified the region of interest and place it on the center of the screen, I lift the camera screen and I check what I see on the. So here is the amorphous region that we were seeing on the fluorescent screen. As you can see, there is no signature of this kind of diffraction contrast from here. So this is more or less an amorphous area. What you should do is, once you go to such an area, you press the standard focus twice so that you're at the right focus. And if needed, you just correct the height to see that from the edge of the area, this bright and the dark band are sort of coinciding. So at the location where the mouse pointer is now, it is more or less coinciding. That means I am at the correct focus. Now, using the objective focus knob, I can go under focus or I can go over focus. And what you see here in this window where you have the red circle is the Fourier transform from this area. When you're having the effects of objective stigmatism, this Fourier transform from an amorphous area does not appear circular. Please bear in mind that even here the Fourier transform is not extremely clear, because this is from a microscope with a lanthanum hexaboroid source. On a field emission source, you'll have this a lot more clearer. Your objective is to go to the amorphous area, go to the right focus, go slightly under focus till you see an edge, and you click on objective stigmation knob and try to make it as circular as you can. On this particular tool, it is not very clear, and I'm not sure if you can see it on the camera screen right now, but at this point it is more or less coincident. One of the ways in which I know if the stigmatism is corrected is when I go far out of focus. I should not see any streakiness in the amorphous area. So I'll try to make it as circular as possible, the Fourier transform, and hopefully the ring is a little more clearer now. So I see some kind of an ellipse in this direction. It has to be made circular. I'm not sure if it is very evident in the video recording here, but what you can see is from the edge of the sample, when I go out of focus or when I go either over focus or under focus, it appears more or less that the movement is in one plane. So this is an indication where the objective stigmatism is more or less corrected. Owing to the limitation of this particular tool with the lifetime of the source that it is right now, the amorphous ring is not very clear, but we'll soon move on to a field emission gun TEM where this will appear more clearer, and that is a more appropriate tool for doing high resolution imaging. But nonetheless, because we've oriented this and we've tried to get some sort of corrections done, let us see if we get some lattice fringe images from this microscope. So I've just shown the procedure of sort of correcting the objective stigmatism and aligning the HT wobble. Once you've successfully done these, and if your grain is oriented in the zone axis, you'll be able to get some lattice fringe imaging. Anyhow, I'll show this in more detail on the other microscope. Now I'll show you how to operate the microscope to get some lattice resolution images, or in other words, high resolution TEM imaging. What we do here is, after correcting all the other condenser stigmatism, condenser aperture, bringing to the right eucentric height, I need to search for an amorphous area on the sample. I bring the amorphous area into the field of view and the feature of interest into the field of view. And more importantly, please remember that I have to first orient the sample along the right crystallographic orientation. I've shown you a few videos where tilting is done. You have to identify the direction of your X tilt and the Y tilt, or alpha tilt and beta tilt. Orient your crystal into a low index zone axis, and then go to the amorphous area and start correcting for objective astigmatism. Also, before you do the objective stigmatism correction, you have something called as the HT wobble correction, or in the Thermo Fisher microscopes, you call it as the rotation center alignment. So, or you also have the voltage centering and current centering on the other instruments as well. So we do that, and once you do this, so in order to correct for the HT wobble, what I do here is I spread the beam. I go to a magnification of over 100,000x. In this case, I've gone to 120,000. It is not extremely important. Beyond this kind of a magnification is okay. It is purely depending on your convenience. I bring a feature of interest into the center, and I click this HT wobble button, and you see that the feature of my interest should move in a single plane. Most of the time, this correction is more accurate when done on the small screen on the fluorescent screen camera, or on the fluorescent screen here through the binoculars, but you can also do it here. So after I've selected the HT wobble, I need to turn my stigmation knobs and the deflection knob, and I see that so if you see here, the corners from the area, which is the edge of this ring here, and the central feature is more or less going along the z-axis of one plane in and out of the screen. It appears that way. At this condition, you know that the HT wobble is more or less corrected. When I started with, it was also reasonably fine. If you are in this condition, you need not really misalign it. Sometimes you may have a situation where the HT wobble is quite misaligned. Now I go on to an amorphous area, and I go to a magnification about 300,000x or so, and let me bring the amorphous area. It is easier to show the amorphous areas on a cross-grating sample, so for the simplicity of it, I've shown it here. So I bring the amorphous area to the center, and I switch to the CCD camera now. So we've now moved to an amorphous area in the sample. What you see here are the gold grains or nanocrystalline gold particles, and here is carbon on the cross-grating sample. And on the right, you see the fast Fourier transform from this particular selected region. Now what is interesting here is, as a consequence of the contrast transfer function that you have from this particular region, you see the Fourier transform here. In the theoretical sessions, I've already explained to you, as a consequence of aberration and defocus, how the contrast transfer function is going to change, and how the aberrations influence what you see in the backfocal plane, which is corresponding to the Fourier transform of your object. And once I take an inverse Fourier transform of this, I form the image. Now we use this principle, and we take the Fourier transform from an amorphous area, and we are correcting using the quadrupole or the hexapole beam deflectors here. So by using the stigmation coils that you have when you're looking at the Fourier transform of the amorphous area, by correcting for the stigmation coils, you're trying to make this as circular and symmetric as possible. I go to an amorphous area, and at zero defocus, I see an image like this. In an ideal scenario, when I'm at the right focus, I should see a ring with almost infinite diameter here. But because there is some aberration now, and in order to correct the aberration using the objective stigmation coils, I need to go to some defocus value. If I go to a defocus value of around 500 nanometers approximately, I see a few rings like this. So I now select the OL stigmation knobs, OL stigmation button, and then by turning the deflection or stigmator knobs, I try to make this as circular as possible. Now I go to the right focus. When I'm at the right focus, you see on the image on the left, the contrast is minimal, and I do not see any rings here, or I see a ring of an infinite diameter here. Now I go slightly over focus, and when I'm going over focus, I see that the pattern here is slightly more elliptical with an elongation in the y direction. So I also try to make it as circular as possible on the y-axis direction as well. So I intentionally go over and above the right focus a couple of times to ensure that the rings that I see here are concentric, and this gives me an indication that the objective lens stigmatism is sort of corrected. Once I've corrected for the objective stigmatism, please remember to switch off the objective stigmatism button, or you unpress the thing, because you never know, accidentally if you deflect the knob or the coils here, you'll be uncorrecting the stigmation that you've just done. and go to the area of your interest, and you can start zooming in and you start seeing the lattice fringe images. Typically, once you go to a magnification of around 600, 500 or 800,000x, you start seeing some of these features. So as you can see, I am more or less at the right focus, and to improve the contrast, I'll slightly go under focus, and I have to change the exposure time here. Let me put it as half a second or 500 millisecond, and let me get a snapshot to get you some high resolution lattice fringe imaging. Please bear in mind, what you see here are actually lattice fringes and not really images from the atoms themselves. These are projections of atomic columns which are arranged in some kind of a crystallographic orientation, and you do not know really the exact position of the atom. You have to obtain a through focus series from such a specimen, and you have to do a mathematical reconstruction to know the exact position of the atom. A lattice fringe image or a high resolution image is strictly not the image of an atom within a lattice. It is only a projection, and it is a phase contrast image, and you see this fringes here. So that is how you get high resolution images. Here is the aluminum specimen oriented along 110 zone axis. If I save this with a slightly longer exposure time, let us say with 100 milliseconds, and now if I correct for the gamma here, you can notice that there are some superlattice reflections here. So now I can do high resolution imaging on this particular grain to see how these superlattice reflections which are coming here from the precipitates would look like in high resolution. Or I can actually put in an aperture around one of these and only highlight these particular precipitates. So we'll start with imaging these precipitates, and then let us do a high resolution TEM imaging. Okay, so now after orienting the specimen into the zone axis, what we'll do is we'll try to obtain some high resolution images from this particular area. So for this, again, I have to do a couple of corrections. So firstly, starting with the condenser astigmatism and aligning the condenser aperture. It is not essential to align the condenser aperture and make a completely circular shape when you're doing high resolution imaging. There are some modes where you intentionally offset the condenser aperture and make it more parallel. And right now, let us correct it. I see that there's a lot of condenser stigmatism, so let me move this to the center, and I'll click on CL stig, and if I press the knob and this bright green LED appears behind, that means I can do coarse adjustment, and I try to make it as circular as possible so that my condenser stigmatism is now corrected. And the next step is checking of the wobble. I'm assuming the HT wobble is pretty stable, and it appears that way. So there is no need to correct for HT wobble now. And the next step is correcting for objective stigmatism. For correcting objective stigmatism, I should go to an amorphous area, and I should stay somewhere around 200 or 300,000x. So typically edge of any specimen, whether it is electropolished or iron milled, one of the very closest points to the hole, you'll always find some amorphous area. So let me show you the CCD screen now. And you see this edge here. This is the Fresnel fringe because you're not at the right focus. So I'll press standard focus once, and then let me try correcting the height to see if the edge. So I'll do it in super fine mode, and as you see, the white border from the edge has disappeared, and I'm close to an amorphous area. So let me obtain a Fourier transform from this particular region. So you could do a Fourier transform from the whole image, but in this particular microscope, in this particular camera, the sensor and the pixel aspect, the camera aspect ratio is not 1:1. If you're using a Gatan camera, you should select the Alt button and then use something which is to the power of 2 to the power n to get the fast Fourier transform. But on this microscope, if you just hold shift and get a near square image like this, you see the power spectrum or the CTF or the FFT from this region looks like this. So we'll go to an amorphous area and we start correcting the objective stigmatism. We are more or less at the right focus. So I have to go, this is when I go under focus, and this is when I go over focus. You can see that the major axis of the ellipse that you see in this spectrum here is not coinciding on either side. What I'll do is I'll just increase the exposure time to make this a little more evident. So if I select the OL stick button now and I make this as circular as I can, and let me change the focus and go under focus now, I see very slight aberration in one of the directions around the 11 o'clock direction. So when I go on either side of the focus, over focus or under focus, when the ring is circular, that means I've more or less corrected to the best of the abilities with this microscope. And now I go to the area of our interest to get a high resolution image. So I'm just moving to the area now, and yeah, I've brought the area of our interest into the field of view, and let me go close to the edge so that it is slightly thinner. And if I correct for the focus now, so if I go to the sort of the thinner area of our interest, you can see the lattice fringes from within the precipitate and adjacent to the matrix as well. Should get them. One of the roughing pumps is now running in the background, so We'll have an issue in getting the best resolution, but I'll go slightly under focus and have to change the exposure time now. So here is one of the precipitates which is embedded in the aluminum matrix, and here is a lattice fringe image from the precipitates. So you can see that there is some sort of an orientation relationship between the precipitate and the matrix here, and when I change the focus, I would actually see that the contrast here at the edges is also changing. And in fact, what you see here is just the fringe image, and to get the actual positions of the atoms, you need to obtain a through focus series, and this is how you do high resolution imaging on the F200 microscope.